All right, let's get started with section 7.1, our first section about exponential functions. And for this one, we're going to take this example where we say that on Monday there are 100 E. coli bacteria cells in a petri dish, and every day the number of cells doubles. That means it gets multiplied by 2. And we're going to use P of t, which I accidentally called f of t here, whoops. P of t is going to be the number of cells after t days. So you input the number of days after Monday, and the result here will tell you the population of the cells, the number of bacteria that there are in this petri dish. So we're going to start by filling in the table, and then once we see what are we doing with these t values to get the corresponding outputs, that will tell us how to find a formula for it. So let's start with day 0. Day 0 means the first day that we're talking about on Monday. So on that day there's 100 E. coli cells. That's given. And then the next day, Tuesday, it's going to double. So that is going to be 100 times 2, also known as 200. And the day after that, it's going to double again. So you're going to end up with 400. One thing I want to point out here is that this is not a linear function. In a linear function, the change in y divided by the change in x would be constant. But in this case, when you go from 100 to 200, from t equals 0 to 1, that's a slope of 100. But then from 200 to 400, you get a slope of 200, because you end up doing 200 divided by 1. And so delta y over delta x is not constant here. So it's not a linear function. Now, so at least we know it's not going to be something like f of x equals mx plus b. So it's not that kind of function. Let's see how it works. If we keep going here, you can just keep doubling it and get 800. But what I want to see is what's the connection between these values of t that we have here and these numbers. T tells you how many times you doubled it. So what do you do with the number 3? It means you double 100 3 times, starting with 100. So in other words, you could get this by saying, I'm going to start with 100, and then I'm going to multiply that by 2 once. So that 100 times 2 gives you that 200 there. And then it gets doubled again when you get to day 2. And then by the time you get to day 3, it's doubled a third time. So doubling it 3 times is the same thing as multiplying by 8. So you can see this as 100 times 2 to the power 3. 2 to the power 3 is 8, and 100 times 8 is 800. And the reason I wanted to do that is because it shows you where the number 3 can show up in this calculation. Likewise, if we did the 400 that way, we'd be doing 100 is where it started, but then we multiplied it by 2, and then multiplied it by 2 again. And so that's also known as 100 times 2 to the power 2. And that way you can see that the exponent of the 2 is the same as the input into the function. So it sounds like we can now think of what if we just wanted to plug the number 4 into something. Well, you could think of it as 800 times 2 if you want, or you could also think of it as 100 that gets doubled 4 times. So I'm going to plug that 4 in there, and 2 to the power 4 gives you 16, and you end up with 1600, just like 800 times 2 is 1600. So it looks like we've got a formula kind of figured out here. It's the same as doubling the previous version, multiplying the previous one by 2, but that's just the same thing as starting with the 100 and multiplying it by 2 this many times. 1, 2, 3, 4, 5. So this would be 2 to the power 5, which is 32. So you end up with 3,200. And if we keep going, we're going to get 100 times 2 to the power 6. 2 to the power 6 is 64, so this gives you 6,400. And then what about day 30? You could think of it as 6,400 times 2 times 2 times 2, and then double it 24 times to get from t equals 6 up to t equals 30. Or rather, let's just use the formula and do it as 100 times 2 to the 30 power. And that's going to require a calculator. So here's the calculator. We're just going to do 100 times 2 to the power 30. And you get this. This means 1.0737. Let's round it off to 4 decimal places, I guess. But remember, the e means to the power 11. So that means this is, it means times 10 to the power 11, excuse me. That's what the e thing means. It's scientific notation. So this really means we're going to move the decimal place over 11 times. So you could write it like that, or you could write it as like 107 billion. Let's see what it looks like once you move the decimal place over that many times. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I need those many zeros there. Okay, so that is a gigantic number, 107 billion. So on day 30, maybe there's actually that many E. coli cells there, or maybe they just ran out of food in the petri dish, and it maybe doesn't really continue growing, doubling like this forever. But yeah, it will increase a lot whenever you have something that doubles every time like this. So what is the formula that we're using here? How are we calculating these output values based on the input values? We're doing 100 times 2 to the power t for all of these. So it looks like the formula for p of t should be p of t equals 100 times 2 to the power t. And this is our first example of an exponential function. It's called an exponential function because the input ends up in the exponent of an exponential expression like this. So that's a sort of general thing, and this will apply to other situations as well. When you have a starting value or an initial value, means the same thing, and that's called 100. And the number 2 here is called a growth factor. So what that means is it's a factor because a factor is something that gets multiplied in general, and that's what you're doing here every time is you're multiplying the previous one by 2. So you call that the growth factor. So in general, let me drag this down here so we can see it here. If you have any old function f of x and the output of the function, that's what I mean by f of x is output. So the output gets multiplied by b every time x increases by 1. That was happening here. These p of t, the output values, are getting multiplied by 2 every time t increases by 1. Then, and if f of 0 equals a, in our case the a is 100, then you can write a formula of this form that will make it happen. F of x equals a times b to the power x. And in this case, A is called the initial value or the starting value. It means the same thing. That's what you get when you plug in x equals 0. And let's just see why that works here. Because if you plug in x equals 0 into a formula like this, you're going to get a times b to the power 0. And anything to the power 0 is always 1. And so that just gives you a times 1. So that's why that number is always going to be what you get when you plug in x equals 0. And plugging in x equals 0 has another name. We call it the y-intercept. That is the y value, the output value you get when x is 0. And the number b is called the growth factor. That tells you how much f of x gets multiplied by every time x increases by 1. So it's going to be the growth factor actually as long as b is greater than 1. Because multiplying a number by something bigger than 1 will make it increase a little bit. So for example, if you do like 200 times 1.01, you're going to get something a little bit bigger than 200. You're going to get 202. But it's going to be a decay factor if b is between 0 and 1. That's going to, for example, if you do 200 times 0.99, it makes it a little smaller, and you get 198. So that will make your output values get smaller when you have a number that's less than 1 here. So that's the basics of exponential functions. We'll do some examples in the next video.